Welcome to the MOOCs course Mechanical Unit Operations. The title of this lecture is Screening. As the title indicates, screening is about the separating. We are discussing about the particulate solids. Particulate solids may be having wide range of size distribution. So, then how to separate them using the screens is about the screening in general. So, we see the details of screening, how to do, what are the analysis processes, how to handle the uniform mixtures, how to handle the non-uniform mixtures, etc. These things we are going to see in this and then coming couple of lectures. So, the screening is separating a mixture of various sizes of particles into two or more fractions. What happens in general from the natural resources, whatever the bulk material that you get, what you need to do, you need to crush them into the smaller fractions so that you can comfortably use them in subsequent operations after pre-treatment unit operations, right. So, one of the pre-treatment unit operation is a kind of size reduction, which is also accompanied by which is also followed by the screening. Screening is one of the kind of important operation, right, that we have seen. So, here what happens, whatever the natural resources or the crude raw material that you get from the natural resources, you crush them into the smaller fractions so that you can comfortably use them in their subsequent operations, in unit operations or unit processes, right. That is what we do by size reduction. But when you do this size reduction or the reducing the size of this bulk material into the smaller fractions, you get the particles of very wide range of size distribution. Some particles may be in a few micron size, 1 micron or 10 microns are smaller particles. Some particles may be in some centimeters, something like this. So, let us say I have drawn here mass fraction versus particle size in mm. You can see some particles are of around 1 micron size, and then there are some particles are of 1 centimeter. So, then distribution is very wide distribution you can see. But what we do, if you do the screening, we can separate this crushed material into the several smaller fractions, so that we can have a separate fractions, individual fractions whose particle size distribution is much narrower compared to this initial mixture whatever we have taken. So, when we do this screening, the same sample we can separate into the several fractions, maybe one fraction of this range, another fraction of this range, and another fraction of this range, another fraction of this range, another fraction of this range, like this. What we have done by using this screening, we have separated the particles into several fractions, and then each fraction is now in having a kind of very narrow particle size distribution, so that you can assign one single average size for this fraction. That is what by using screen we are going to do in general for our applications. So, that is each fraction whatever after the screening we get, that is more uniform in size of particles than in this whatever original mixture. That is what we are going to do by screening, separating mixture of particulate matter into various sizes or various fractions of having different size fractions, right. So, in other words, what we have, the particle size distribution of original mixture may be very broad as shown here in this picture, and then whereas each separated fractions particle size distribution will be very narrow as shown in the subsequent figure like this. So, this is what basically the purpose of screening applied for particulate matters, that is what we are going to have. So, now this is very crudely what about the screening, why should we do, but why should we do the separation based on the size using the screens, is it all important? So, what we do, we see first few generalized kind of situations where the separation by size is required for these particulate matters, and then we see some kind of specific applications examples as well. Separation of materials on the basis of size is important because preparing a product for sale or for a subsequent operation. For a subsequent operation, let us say after crushing you do the kind of separation into kind of smaller fractions, and then you may be collecting only that fraction which is suitable for your subsequent operation. That is for those kind of generalized cases, or sometimes product that let us say you have a fertilizers industries, whatever the fertilizers after solidifying those chemicals, you get pelleted forms or granulated form fertilizers that you get. So, granulated fertilizers are not in a kind of uniform size, and then you may be needing to have a kind of a specified size of fertilizers for a given kind of application. So, there also you may need to use this kind of screening for the separation of these material as per their applications. Okay. So, it can be as a kind of requirement for the product, or it can be a kind of a requirement for the subsequent operations in the plant. Likewise, the effectiveness of the size reduction operations can also be controlled by using this size analysis by screening, or to control the effectiveness of size reduction operations such as crushing or grinding. So, whatever the crude raw material that we get from the natural resources, crude raw material that we get, that you reduce into the smaller fractions, smaller size particles by crushing or grinding. Whether those equipment are properly grinding or doing the size reduction or not, that effectiveness of those equipment can also be studied using this screen analysis. We are going to do that one also by taking some example problems in next module. Probably you may need that equipment crushing material of let us say 0.1 mm size, but either it may be doing very smaller particle size, much smaller, or some micron size 0.001 mm, or some 1 to 1 mm to 2 mm such bigger size also it may be doing. Is it doing proper duty or not? Or for a selection of equipment also this kind of analysis is required. If let us say if you are not sure which kind of size reduction equipment should you use for crushing the material, reduced material of your requirement, right. Let us say you do not have information, then you try different size reduction equipment, and then you take that sample and then do the screening, and then subsequent size analysis of the individual fractions, and then you can see which is going to be very beneficial for you. That way also for selection as well as the controlling the effectiveness of this size reducing equipments is also done by this separation based on the size using the screens. Also, to determine the value of a product for some specific applications, usually marketing oriented. For a marketing purpose, let us say some food product or some kind of pharmaceutical product, you need to have the chemical, that final product or the chemical of specified size. In such cases also you may need to use the separation by size using the screens. So, these are some general kind of situations where we may need a kind of size separation or the separation based on the size using the screens. But now we take a few examples, specific examples what way they are useful. Let us say size of coal particles is a basis of its classification for sale. In general, coal is obtained by the mining. When you do the mining, open cast mining or underground mining, you get the coal. That coal is in a kind of big lumps or in a small particle size, the entire things are there. Usually those coal has been taken into the kind of the transporting equipment like lorries or conveyors, something like that, belt conveyors, etc. They will be from the mines. By using the belt conveyors, they will be taken out, and then once they reach the surface, from the surface they taken to the industry where they can be used by the trains or lorries, etc. Right. So, when it comes for use, let us say you are using for the coal combustion so that you get the energy. So, there you cannot have a kind of bigger size particles for this kind of process, otherwise combustion may not be effective. You cannot also have a kind of very fine coal dust particles having the 1 mm or even smaller than some nanometer scales. So, those kind of particles may also be not suitable for the combustion. Probably you may expect to have a kind of particles something like 500 to 900 microns size, that is going to be very much suitable for you. So, there also you may need to do the size analysis or separation based on the size, and then the market value for that particular coal which is having specified size may be having more value. That could be one kind of applications. And then certain equipment such as stockers, etc., they need definite limits of size for successful operations. Okay. Then also in concrete mixture making, so we have the cement, water and then sand gravel mixture we take in a kind of equipment, we mix them and in order to get the concrete mixture for construction purpose, right. So, for that you might have seen the sand as well as the gravel particles are screened at the construction site, so that only a specified size are only taken into the this container where the concrete making is done by using the cement and then water. So, there you need to have a kind of specified size of the sand, specified size of the gravel, then only you can have a kind of a proper concrete which will provide a proper strength and which will require a less cement, etc., that is possible. So, here also in this kind of construction purpose also the size separation by size is also becomes kind of important component. So, when you have this sand and gravel for concrete, only properly blended series of sizes will provide you the most dense packing requiring minimum amount of cement and then securing the greatest strength without any voids. Okay. So, here also screening is a kind of important application. Then coming to chemical engineering, most of the heterogeneous reaction where the reaction is taking place between solid and fluid, the specified size of the solid particles are required, because the rate of these heterogeneous reactions are in general proportional to the surface of particles. So, then here also you are supposed to maintain a kind of specified size of particles which is participating in reaction with a kind of fluid. So, here also you may need to have a kind of a size analysis or size separation based on the screening. Likewise, if you see some more examples, as I already mentioned, in order to control the rate of combustion of coal combustion. So, where ability of controlling the grinding operation to produce coal material of definite size is very important. Similarly, we have a settling of Portland cement that must take place within a specified time. So, accordingly it is necessary to specify certain size limits for those kind of Portland cements also. Then the hiding power of a paint pigment is indicated by size, which depends upon the projected area of the particle. So, then here also you may need to have a kind of size analysis or separation based on the size. So, if you see the applications specific applications also n number of applications are there. So, a few of them I have listed out here. Then what equipment should we use for this screen analysis? So, in general these screens are used for this kind of screening operation where the separation based on the size is taking place for a given particulate matter, right. So, what are the screens? Screening equipment may take the form of stationary or moving bars punched with metal plate, oven wire mesh, sieves, etc. So, we have in general metal plates like this. So, where they are punched with small kind of holes or this holes of desired size, and then these the hole opening is almost uniform in the entire this plate, and also the distance between these holes is also maintained uniform in general, right. Then we also have a kind of oven wire mesh like shown here. So what we do, you take wires and then you do the oven wire meshing here as shown here, like kind of sieves. So here the diameters of wire and then openings of the wires are being very closely specified in general. Also the spaces between the individual wires of the screen is known as the screen aperture, which are square in the shape. The screen aperture shown here, they are square in the shape, and then that opening is known as the screen aperture. Okay. So, what we do these things? These screens usually form the bottoms of metal pans about 8-inch diameter and then 2-inch height. They are something like this. We have a kind of metal pans like this as shown here, these metal pans. Right. So, the diameter is usually 8 inches and then depth or height is usually 2 inches. The screens whatever are there, they form bottom of these pans. Here in this bottom usually we have the screens, right. So, whatever the screens that I have shown previous slide like this, they are placed here like this. I have shown a kind of 2D image. Now, this particular screen is taking place at this bottom plane. So, that will be occupying this bottom space here. So, whatever the screens are there, they are taking the bottoms of these metal pans. So, these metal pans are in general 8-inch diameter and then 2-inch height. Okay. So, we can have a different size screens as a kind of bottom for different pans. So, then we have n number of pans and then each pan is having a screen at the bottom. right. So, the opening of each screen is different from the other screen, so that we can do the size separations, right. Okay. Then the sides of these pans, whatever drawn here, metal pans, are designed such a way that we can place one onto the other. So that the sides of these pans are designed such that the bottom of one sieve can be mounted on the top of the next screen. So that we can have these n number of screens one on to the others, and then we can do the size analysis, fine. So, for the screens, the mesh number is also provided. Usually the screen is designated by the screen aperture opening, what is the opening size, that is the one way, and then other way is the mesh number. Mesh number is let us say this is 1 linear inch space here. So, this if I draw it here, this linear inch space expand here. So, this is 1 linear inch space, linear inch dimension in the screen. Okay, I have expanded here. Within this 1 linear inch or per 1 linear inch dimension, if you have, let us say, 10 openings like this, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 like this, then what we say, this particular mesh is given as 10 mesh number. Let us say in the 1 linear inch dimensions, if you have a kind of 20 openings like this, then we can say, we can call it as a 20 mesh number. And then likewise, if you have, let us say, 100 mesh openings in a given linear inch like this, so then 100 openings are there, then you can call them as a kind of 100 mesh. So, what is the size of this square aperture? Then that would be 1 by 100 minus diameter of the wire that has been used for constructing this particular screen of 100 mesh number. So, that would be 0.01 minus this diameter of wire. That will give you the screen aperture opening, size of the screen. So, the screens are in general, they are given by the mesh number or they are designated by the screen openings. So, we can call them based on their so and so screen, let us say 3 by 4 inch screen opening, or 1 by 2 inch screen, or 1 by 16 screen inch, like that. By size also we can say that size indicates the opening, screen aperture opening size indicated by that size 3 by 4 inch or 1 by 4 inch, etc. right. The same screens can also be designated by the mesh numbers. So, that mesh number indicates the how many number of openings are there per linear inch dimensions. Okay. So, either way these screens are designated, labeled. This is about the individual screens. How to do the screen analysis? So, in this screen analysis, usually what we do, screening is accomplished by passing a crust material through a surface provided with openings of desired size. That is what the screen about in general. So, in the screen analysis, a set of standard screens arranged serially in a stack with the smallest mesh at the bottom and the largest one at the top. So, that is something like this. So, now this is the bottommost one, is a kind of a pan which is not having any kind of opening here, right. So, whatever this is a pan kind of thing, bottommost is a kind of a pan. So, here, so whatever the finest material is there, that will be collected here. So, that will not pass through. So, then on this pan we will have a metal pan of having a kind of certain opening like this, that will be arranged. Okay. So, on this metal pan we can arrange, we can mount another metal pan of this screen, having this particular screen as a kind of opening. Likewise, one onto the other we can arrange these n number of metal pans with screens at the bottom are arranged on a metal stack like this in a serially. How they are arranged? The finest opening one is at the bottom just about the pan, and then coarsest opening one at the top. So, that is at the bottom you have to take a pan without any opening, so that the finest material can be collected at the bottom. Onto this pan you can have a kind of a metal pan with a screen at the bottom. That screen is having the finest opening of your requirement. Then onto this one you can have the another pan kind of thing, which is having a kind of a opening, the screen aperture opening larger than the bottom one. So, on this one we can have another screen whose opening is a kind of larger than this bottom one. Like that we can arrange one onto the other, n number of screens we can arrange, and then the topmost one would be having a kind of a largest opening screen aperture size. So, that means the screens has to be arranged such a way that the finest should be at the bottom, and then gradually this screen opening should be in an increasing order, and then largest opening screen would be at the top, right. Then sample is placed on the top screen and stake is shaken mechanically for a definite time of about 20 minutes and in general. So, whatever the crust material is there, that you take here, and then this set, whatever the setup is there, you mechanically shake it for a specified time, 20 minutes or 30 minutes, so that whatever the particles smaller than the opening of this screen, they will pass through. Similarly, particles smaller than this particular opening, they will also pass through, and then similarly particles whatever the things smaller than this screen opening, they will also pass through here this screen. Like that, finer particles are passing through, and then larger particles are retaining. So, that is, whatever the, let us say the top screen it is having opening 1 mm, let us say. So, particles which are having size more than 1 mm will be retained on that one. Particles having less than that size 1 mm, that is 0.89 mm, 0.8 mm or even 1 microns, 2 microns, all those things will pass through here. They will not be retained on this screen. Like that, on the second screen, let us say its opening is, let us say 0.5 mm. So, whatever the material that is larger than 0.5 mm but smaller than 1 mm, they will be retained on this second screen, and then particles which are having size smaller than 0.5 mm, they will be passed through. Okay. Like that, let us say if the next screen size is 0.1 mm. So, here when the material comes here, while the shaking process is going on, whatever the material that is having size smaller than 0.1 mm, that will be passing through the screen, but whatever the material larger than 0.1 mm but smaller than 0.5 mm would be retained on this particular screen. Like that, each fraction, depending on the sample and depending on the size opening, each fraction there will be some material will be collected. Sometimes it is possible that based on the sample, one particular screen there will not be any material also. So, let us say this case itself, if your sample, in the sample you do not have any particles more than 1 mm size, it is possible that on the top screen you will not be having any material, because your sample whatever I have taken, that is having the size that is not having any particles more than 1 mm, all the particles are having less than 1 mm only. So, all the material will pass through this screen which is having 1 mm opening, that is, so that on the top there will not be any material. Likewise, it is also possible for the intermediate screens also, in between also there may be some screens where there is no material present at all. So, this is how we do it, right. Now, the material that is passing through is known as the undersized material. So, material that is retained on a screen is known as the oversized material. And then in this screen arrangement, so each screen is given a title as a screen increment. So, on each screen increment we get some amount of material, that some amount may be 0 in some cases, and then we tabulate it. And then let us say the material, whatever the material that is collected on the second screen having opening 0.5 mm. So, that material, this size of that material is expected to be between 0.5 mm to 1 mm only, right. So, that is a kind of narrow size distribution, but not all particles will be having 0.5 mm, not all particle will be having 0.99 mm, because it has passed through the previous one. The distribution may be between 0.5 to 1 mm. So, we do not, there may be particles of different sizes, but what we see that the distribution is very narrow, very narrow. So, then the average size, we can assign the average size for this sample here on the second screen as 0.5 plus 1 divided by 2. So, 1.5, that is 0.75 mm, we can say that is the average dimension of that sample retained on the second screen. Like that for all the screens we can do. Okay. Now, particles retained on each screen are removed and weight and the masses of individual screen increments are converted to the mass fraction. So, these screens arranged here, they are usually called as increments. Whatever the material that you collected on each screen, after mechanically agitating it for or shaking this stake for 20 minutes or 30 minutes, you stop the operation, collect the material from each screen, weigh them and then convert them into the kind of mass fraction and then tabulate them against to their average particle size against each screen increment. So, that is how the screen analysis procedure, that is the procedure that we should follow. Then that data may be used for kind of subsequent kind of analysis like separating fraction, each fraction having different fractions having average size, average dimension or average size, any term can be used. Then what we can do, we can also calculate what is the total surface area of individual fraction as well as the total surface area of the entire sample, that can also be calculated. So, those things we are going to do in the subsequent lectures anyway. So, but this is the screen analysis. This information would be used for those subsequent calculations like obtaining the total surface area of sample or the surface area of the individual fractions. Likewise, we have the volume mean diameter, surface mean diameter for the total samples. So, how to obtain those different types of mean diameter like volume mean diameter, surface mean diameter, surface to volume mean diameter or Sauter mean diameter, these kind of things are there. So, those can be calculated based on the results that you get from this screen analysis. Okay. So, whatever the equivalent diameters in previous lectures that we have calculated, equivalent diameter or nominal diameter or sphericity etc., they are with respect to the single particles. As I mentioned there also, they are with respect to the single particles, but now this is for the sample which is having several millions of particles. Then for them how to do the analysis, how to fractionate them, and then each fraction how to assign a kind of equivalent diameter for that entire sample, equivalent like volume equivalent diameter, surface equivalent diameter, those kind of things in addition to the surface area of the individual fraction as well as the total surface area of the sample, those things we are going to calculate in the subsequent lectures by using these results that you get from this screen analysis. So, particles that pass the finest screen are caught in a pan at the bottom. So, in the pan whatever the particles you will get, you are expected to have the finest particles retained on this pan, and then coarsest particle you are expected to be retained on the top screen in general, okay, depending on the size and the screen opening and then depending on the sample as well. Okay. Right. Then is it true that let us say this 0.5 mm screen, whatever the sample is there, so that sample, is it true that the entire sample within that range is going to have the size range only between 0.5 to 1 mm? But that is not true in general. That is not true in general, because you take the solid sample, so many of particles in general. So, sometimes very fine particles which are having size smaller than 0.5 mm may be trapped between the other particle, bigger particle kind of thing. So, that may not be passing through 0.5 mm. So, it is possible that the material that is retained on this particular screen, that may be having size smaller than the 0.5 mm also, that is also possible. Sometimes it is also possible that particles which are having size larger than this 0.5 mm, that may also pass through the screen, that is also possible. If your screens are having a kind of wearing kind of thing, the mesh is broken somewhere, something like that, those kind of things are also possible. Anyway, that will decide the effectiveness of the screen. So, those effectiveness of the screens also we are going to see, there are several kind of parameters that are going to have influence for these kind of results, where particles finer size are also being retained on a kind of screens, and then particles bigger size may also be passing through. So, there are several reasons, we are going to see them also. So, these results, what we do? The results of the screen analysis are tabulated to show the mass fraction of each screen increment as a function of mesh size range of increment. So, let us say mesh size increment 10 mesh, what is the mass fraction you got? You can tabulate. Then next row, what you can have a 14 mesh, what is the mass fraction? Likewise 16 mesh, what is the mass fraction? Likewise in a kind of increment order, you can include 100 mesh, what is the fraction of material that you retain, that you have to tabulate. And then since the particles on any one screen are passed by the screen immediately ahead of it, two numbers are needed to specify the range of increment, right. So, one for screen passing through or through the fraction passes, and the other one on which it is retained. That means 14 by 20 screen means that is through 14 mesh and on 20 mesh. The different types of representations are there. This can also be represented as minus 20 plus 14, as I mentioned, that also we are going to see some in the next slide. So, this information what you do, tabulate as columns, one column for the mesh, next column for the screen opening, that is the aperture opening for that particular screen. Let us say 100 mesh, what is the aperture screen opening, that you will be writing in screen opening DPI column. Next column is the mass fraction xi, let us say that is the, what is the mass fraction, that is the weight of the material retained on the 100 mesh. Let us say if you are taking 100 mesh as example, weight of the material that is retained on 100 mesh divided by the total weight of the sample, that should be written as a kind of mass fraction retained on that one. And then average particle diameter increment dpi bar. Let us say the material that is passed through 50 mesh and then retained on 100 mesh. So, whatever the screen aperture opening of 50 mesh plus whatever the screen aperture of 100 mesh divided by 2, that arithmetic average of these two screen opening, that should be a kind of average particle diameter in that particular increment, that is given as dpi bar, like that you have to calculate. This information now you can use for subsequent analysis for their different types of size representation, or for surface area of individual fraction as well as the surface area of the entire sample. So, how to represent these size fractions? There are three different ways of representing these size fractions. So, first, average size of crust material, whatever it is there, which has passed through one screen and retained on a screen having smaller opening, is the arithmetic average of two screen openings, and it is known as the average dimension or average diameter or average size of the sample. Different terminologies have been used for this kind of representation. Then material that fails to pass through the screen or retained on the screen is referred to as oversize or plus material. Similarly, material that passes through the screen is referred to as undersize or minus material. Okay. Based on the sample, some material may be passing through, some may be retaining based on the size of the screen as well as based on the sample that you have, right. Whichever has passed through, that we call as undersize or minus material, whichever has been retained on the screen, that we call it as a kind of oversize or plus material. When more than one screen used and more than two fractions are produced, then various fraction may be designated according to openings employed in making the separations. And then these designations, there are three different types of indicating size fractions are there. Let us say you have three screens, right. So, one is the size 3 by 4 inch, another one is kind of 1 by 2 inch, another one is 1 by 4 inch, and there is a pan, something like that. So, oversized material is the one that is retained on the 3 by 4, that is the coarsest opening screen, undersize is that is the collected below that 1/4 inch whatever the pan is there, that is the undersize one. Okay. There is a representation for this one. Let us say whatever the material retained here, so you can, there are 3 methods, 1, 2 and 3 ways of representing is there. So, oversize you can simply write 3/4 inch or plus 3/4 inch like this, right. So, whatever the material that is retained passed through 3/4 inch and then retained on 1/2 inch, that you can represent it in 3 different ways, that is 3/4 inch on 1/2 inch or minus 3/4 inch plus 1/2 inch or 3/4 inch by 1/2 inch. So, that indicates that material passed through 3/4 inch, but retained on the 1/2 inch. So, there is another whatever the material that has passed through 1/2 inch and then retained on 1/4 inch, similarly that through fraction intermediate ones we can call them as a kind of through fractions. So, now here the finer particles are there. So, that we can write it 1/2 inch on 1/4 inch minus 1/2 inch plus 1/4 inch. 1/2 inch by 1/4 inch. These 3 different ways we can represent. Okay. So, likewise finest one, whatever the things they are passed through 1/4 inch screen also, they will be much smaller and they will be retained on a kind of pan like this. So, for them, since it is undersized, so here there is no representation. In the second one, minus 1/4 inch or 1/4 inch by 0 inch. 0 inch stands for the pan without any opening. So, these 3 ways of representing is also is there. So, the same representation, the similar way of representation you can do using the mesh number as well. Let us say you have a kind of a 10 mesh, 14 mesh and then 20 mesh in place of inches. Then you can write here in the first case, let us say this should be simply 10, this should be plus 10, this should be plus 10. Say, I do not mean that this 10 mesh is having a 3/4 inch opening, just a kind of representation only. The same representation I wanted to show in terms of mesh number. So, then I am using this roughly the other numbers. Okay. They do not indicate the same opening as 3/4 inch, 1/4 inch or 1/2 inch as written here. Okay. So, now here what we write 10 on 14, something like this. Here minus 10 plus 14, here 10/14, then here 14 on 20, then here minus 14 plus 20, then here 14/20, then here minus 20 or 20/0 or 20 by pan, something like that you can represent. This 0 indicates for the pan. So, if the same representation you can do using these mesh numbers also, either you can do the using the openings, mesh screen openings in terms of inches or centimeters, or you can show them, represent them in terms of the mesh numbers like 10 on 14 or minus 10 plus 14 like that. So, these are the different types of indicating of size fractions are there. As I already explained, the same representation can be done with mesh numbers also. So, can the screening be different, dry screening or wet screening, something like that? Yes, it is. So, the material screening can be dry or wet. Dry screening is the one where the treatment of material containing a natural amount of moisture is treated as it is. So, whatever the raw material, that crude raw material from the nature you get, you crush them and then you do the size analysis using the screen as it is, or you can dry them, then you do the screen analysis using the screens, that is also possible. So, if you use them as it is, including the natural amount of moisture that material is having, or after proper drying also you can do the screening. So, this method of doing the screening is known as the dry screening. Sometimes what happens in your samples, too many of finest particles are there that you do not want in your case, in your representation, or sometimes what happens based on the samples, those finest particles are of very much higher value. So, as I mentioned, sometimes even the finer particles may not pass through the coarse openings, because they are being retained between the particles or whatsoever means by the, or sometimes because of the blocking of the screen openings of coarser screen apertures, etc. Because of those reasons, sometimes it is happens the fine particles may not pass through the bigger openings, or the openings whose opening size is bigger than the particle size. Under those conditions also those particles may not pass through, but those particles are having higher value for you. So, then what you do, you can use water. You can use water operation, the screen operation in which water is added to the material being treated for the purpose of washing the fine material through the screen is known as the wet screen. Either it may be obscuring the process, it is not useful for the process, or those fine particles are having much more value than the other particles, then also this wet screening is kind of important one. Then size analysis of uniform mixtures. So, let us say if you have a mixture of uniform size, the particles, all the particles in the sample, you have a particle size is uniform or almost uniform, that is dp bar, something like that, or dp. Then it is easy to do the size analysis. So, first we do the size analysis for uniform mixtures, then we go for the size analysis of the non-uniform mixture subsequently. So, what we have a sample of uniform particles of diameter dp, then the total volume of the particle should be m by rho p, because now the particle in these uniform mixtures, the particle size is uniform, all the particles are having the same size or almost equal size, okay. If not exactly the same size, they are very much close to each other. So, then under such conditions, if the mass of the particles, if the mass of the sample you know, and then you know the density of the particles, then you can know the total volume of the particles by m by rho p. So, m is mass of the sample, rho p is the density of the particles. So, for these particles they may be uniform size, but you may not be knowing their sphericity. So, then particle shape sphericity you can calculate using the pi s is equals to 6 Vp by Sp dP. This is already we have done. You need to do only for one particle only, because now all particles are having same size. So, then you take one particle, you measure its surface area, you measure its volume, then you get the dP is anyway no, this particle shape you can calculate by 6 Vp by Sp dP. Now, can you have a kind of method to find out the total number of particles in this particular uniform mixture? It is quite possible, because for you now the total volume of the sample is known, m by rho p is the total volume of the sample, m is the mass of the sample. Now, you know the volume of one single particle. So, what you do, total volume of the uniform mixture or the total volume of the sample which is having the uniform particles divided by the volume of one single particle, if you do, you get the total number of particles present in that sample. So, m by rho p is the total volume of the sample, and then Vp is the volume of the single particle, right. So, then you can go the you can get the number of particles present in that particular sample. Then total surface area of the particle, how can you know? Once you know the total number of particle, you can measure the surface area of one single particle, and then you multiply that number by the total number of particles that you already got it. So, then you will get the total surface area of the sample. So, that is A is equals to n into Sp. N is nothing but m by rho p Vp, and then from the sphericity definition, Sp is nothing but 6 Vp by pi s dP. So, this Vp is cancelled out. So, we have 6 m by pi s rho p dP is the total surface area of the sample for that uniform mixture. This is true only for the uniform mixture, but for non-uniform mixture we are going to use it as a kind of basis for each individual fraction, because now after doing this screening, on to each screen increment, whatever the sample that you have, that is having a kind of uniform size, that is what your assumption, right. So, that uniform size, so then you can say that the individual fraction that you get on each screens, that is a kind of individual uniform mixture, then you apply this principle and then add them together to get the total surface area of the sample. So, the size analysis of uniform mixture that we have done today, and the next lecture, subsequent lecture, we will be doing the size analysis of non-uniform mixtures. The references used for this particular lecture are given here. The unit operations of chemical engineering by McCabe, Smith and Harriet, then unit operations of particulate solids, theory and practice by Ortega Rivas, then Carlson and Richardson's chemical engineering series, second volume by Richardson and Harker, transport processes and unit operations by C.J. Giancopoulos, unit operations by Brown et al., and then introduction to chemical engineering by Badger and Banchero. These are the reference books that I have referred for this lecture preparation, but primarily the sources are given in these three and then this fourth book. Thank you.